Now that we have the basics of logic and proofs, we move on to naive set theory. Why naive? Naive set theory is the set theory we use in everyday mathematics. So, it gives us a basic informal language. Now, the real set theory, and we call that axiomatic set theory, when we put that together with formal logic, we have the study of the foundations of mathematics. So, logicians and set theorists concern themselves with whether the rules of mathematics make sense or not. We're not interested in that. For us, we just want to develop language. Now, to start, we have definition of a set. Here we'll be informal and just call it a collection of objects. So we'll usually know sets when we see them. For instance, we have the natural numbers. So we'll just take the positive integers. So 1, 2, 3, 4, and so on. Depending on your book, 0 may or may not be in there. From there, we can get the integers. So we'll take natural numbers, we'll put in 0, and then we'll also put in the negatives. From here, we can go to the rational numbers. So we'll take the integers, then we'll also include all fractions. From here, we'll go to the real numbers. There, we're taking all the rational numbers, and then we'll include all the irrational numbers. So we'll throw in things like square root 2, e, pi, pick your favorite irrational number, and it's a real number. Now, we have addition, subtraction for some of these sets. So one thing to note, a set doesn't have to actually come with any structure up front. It's just going to be a collection of objects. Now, one thing we could talk about with a set and a given, what we call an element of a set, is whether that element is in the set or not in the set. So another definition, if we have an object X in our set capital X, we'll say that X is an element or a member of capital X. And then we write this like this. Now, if our element X is not in the set, then we just use the same notation with a slash to denote the not. You'll note, if I want to describe sets, it's going to be very cumbersome to list all the elements. So we want to take a look at what we call set builder notation. Now, what we do is, we're going to have two pieces here. So we're still going to use the braces to describe the set. This says we have a set. And then I'm going to have either a bar or, a colon. So it's just going to depend on what your source is. The idea, here we're going to describe the actual elements that show up, and then in our second part, we're going to have the conditions that limit what elements show up here. So for instance, for the rational numbers, instead of listing every rational number, instead what I could do is just write down all possible fractions like this, and then I just give the conditions. So we know that P and Q are going to be integers, and we can't have Q equal to 0. Another example, we take the complex numbers, build them out of the reals. So all the elements here are going to be the form x plus I, y, and the condition is going to be that x and y are real numbers. Now, one thing to note about our notation for sets, first, the order doesn't matter. And we also have, if you have any repetitions, you can just remove them. So the set 1, 1, 2 is the same as the set 1, 2. We could generalize the notion of membership in a set to ask, when is a set inside of another set? Definition, x and y are sets. We'll say that y is a subset of x if and only if, whenever x is in y, we also have that x is an element of x. So that's just saying y sits inside of x. We write this like this. Now, example, take e to be the even integers. So in set builder notation, we have 2 times k, where k ranges over the integers. We also have the odd integers, which I'll call O. Here, we'll have 2k plus 1, where k ranges over the integers. Now, we have that e is a subset of z, the integers. O is a subset of z. E is a subset of R, and so on. Note, E is not a subset of O. Now, we've spent time with constructing proofs, showing when statements are true. How do we show that a statement's false? Well, if our statement has many cases, it's enough just to show that one of those cases fails. That's what we call providing a counterexample. So, this is not an elaborate argument. You just show that it fails in one spot, and then the whole statement is false. So, what we want to do, we want to show that we can find a counterexample to the statement that E is a subset of O. Counterexample that I'll use is 2. So 2 is an even integer, it's in E, but 2 is not an odd integer, so it's not an O. So that's going to be my counterexample to the statement that E is a subset of O. Now, for some pictures of what Gape subset looks like, well, if there's no overlap between X and Y, then Y can't be a subset of X. If we have overlap, but Y not completely contained in X, like this, okay, then we have Y is not a subset of X. Then the case where we do have subset, Y is going to sit inside of X in the picture. Now note, Y could be equal to all of X, just as long as it doesn't go beyond the boundaries of X. Now, we're going to talk about when two sets are equal. So two sets should be equal when they have the same elements. Formally, okay, with definition, we'll say two sets X and Y are equal, okay, written like this, if and only if X is a subset of Y and Y is a subset of X. So we think in terms of the pictures, okay, we'll have Y inside of X, but I also want X inside of Y, and the only way that can happen with the picture is if they're exactly the same. Now, with this definition, we have another definition. I'll say that Y is a proper subset of X if Y is a subset of X and Y is not equal to X. So when we say proper, we want a genuine subset, so not taking up all of X. Okay, so here are the pictures. Okay, for the notation, we just use the same notation for subset, but we put a slash through the equals part. Now, for an example, okay, I have that natural numbers are a proper subset of the integers, are a proper subset of the rationals, are a proper subset of the reals, are a proper subset of the complex numbers. Now, let's see how we do a proof to show that two sets are equal. So I'm going to have E as the even integers. I'm going to have O prime equal to 1 plus j, where j is an odd integer. Now, there's not a lot of content here. That's not the point. We want to pay attention to style. We'll see more equality proofs in upcoming talks. So the statement is E is equal to O prime. So in our proof, we're going to need to show inclusion in both directions. Now, okay, so we say proof. Then if I'm going to do E is a subset of O prime, okay, I'll just put this, and it's implied by the way I've written the statement here that we're trying to prove. So we'll start by assuming that we take an element X in the evens. Then I'm just going to use an argument to get to O prime. Now by definition, if X is in E, then X is equal to 2k for some k in the integers. I can rewrite our X as 1 plus 2k minus 1. Then I have to say that 2k minus 1 is an odd integer. So I can do that by another rearrangement, which says that 2k minus 1 equals 2 times k minus 1 plus 1. The reason we need to do this is because of our definition for the odds. So I have to write it as 2 times an integer plus 1. So if we're being strict, I need this statement here. Now, k minus 1 is an integer, so that means this is an odd, which means X is an O prime. So we have our first inclusion. For the other direction, we'll start with an X and O prime, show that it winds up in E. Now, that means if X is an O prime, I can write it as 1 plus j, where j is an odd integer. So that means there's going to be some k in the integers, such that X is equal to 1 plus, and then in parentheses, our odd, 2k plus 1. Now, we can rewrite x as, okay, putting the 1's together, 2 plus 2k, or 2 times k plus 1. K plus 1 is an integer, so that means that x is an even integer and x is an e. So that gives us the other containment. Since we have both containments, that means these two sets are equal. Another important class of examples, we have the real numbers. We'll pick two real numbers a and b, with a strictly less than b. First, we have the open intervals. So for notation, I'll put a and b in parentheses. This is the subset of real numbers x, such that x is between a and b, but not including a or b. For the picture, we'll draw the segment, and we'll have circles at the endpoints, indicating that a and b are not in the set. Likewise, we have closed intervals. For notation, we'll put a and b in brackets. This is the subset of real numbers x, such that x is between a and b, including a and b. So same picture, except we fill in the circles. Note, the open interval AB is a proper subset of the closed interval AB. And we can consider other types of intervals where we let a or b be equal to 1 of, minus infinity, or infinity. So we could call these infinite intervals. Better to call them half lines. Now, for instance, if we took, okay, so I have in parentheses minus infinity to b. So that's what we call the open half line with endpoint b. We would define this as the subset of all real numbers x, such that x is strictly less than b. So note here, we only have a condition on one side of the x. Now, getting back to sets in general, one subset that's of interest is what we call the empty set or the null set. So this is denoted with the null symbol. We could also write it as, okay, we take our braces and we put nothing in there. So it's called the empty set because it has no elements in it. Now, if I have any set x, okay, we're guaranteed at least two subsets. Okay, and they may be the same if the set we're starting with is empty. So first, we're going to have that the null set is always a subset of x. And we also have that x is always a subset of itself. Now, for the first one, if we check our condition for being a subset, let's see what happens. So what we check is, if x is an element of a null set, then we want to show that x is an element of x. Now, you'll note there are no elements in the null set, so to say that x is in the null set is going to be a false statement. So what we have here is an if-then with a false antecedent, which means this statement is always true. So we're going to have this, the null set, as a subset of any set as a vacuously true statement because there's nothing to check. Another construction that's useful, x is any set, we can consider its power set. So that's defined as the set of all subsets of our set x. So for example, if we take the power set of the set with only one in it, where are the subsets? We have the empty set and the set itself. If we take the power set of the set with 1 and 2, we have the empty set. We have 1 by itself. Okay, we call that a singleton set. We have 2 by itself, and we have the entire set. If we take the power set of 1, 2, and 3, okay, again, we have the null set. We have the 3 singleton sets. We have the sets of pairs, and we have the set itself. Now, if you count, you'll note when we have one element, there are 2 subsets. When I have 2 elements, there are 4 subsets. When I have 3 elements, there are 8 subsets. So we can conjecture, but the rule is, if I have a set with n elements, then there should be 2 to the n subsets, or the power set has 2 to the n elements. So that's a theorem. So let's show that. Now, for this, we're going to need the matching rule. What the matching rule says, it's going to give us a method for counting. So if I have m shirts and n pairs of pants, I can combine those to get m times n outfits. Now, the way we see this, okay, well, let's just pick a shirt, figure out how many outfits we get, and then we'll just add everything up at the end. So if I have shirt 1, well, there are n pairs of pants that I could put with shirt 1, so it's going to yield n outfits. Likewise, for every other shirt, so for shirt 2, we'll have n outfits. Shirt M will have n outfits. Now, if we add those up, I want to add n to itself, m times, and that's going to give me m times n. So that's going to give us our matching rule. Now, another thing to note, if we want to extend this, it works the same way. So if I wanted m shirts, n pairs of pants, and p pairs of shoes, we just multiply. So I'll have m times n times p outfits for these 3 items. Now, what's a good way to enumerate the subsets of a finite set? We can list our elements in order. Then, to each element, we're going to assign a 0 or 1. Either that element's not in the set or it's in the set. So, for each subset, we can assign a list of n zeros and ones, and vice versa. So, for instance, if we have set 1, 2, 3, 4, 5, 6, subset 2, 3, 5 corresponds to the list 0, 1, 1, 0, 1, 0. The null set itself is just going to be the list of zeros. Now, how many of these lists are there? So we're going to use the matching rule. So for 1, okay, either it's in or out, so there's going to be 2 possibilities. For 2, there's 2 possibilities, and so on. Using the matching rule, we multiply through. So we're going to have 2 to the n lists of length n of zeros or ones. That means we have 2 to the n possible subsets. So that's our theorem. Now, something to be careful with, okay, when we're working with power sets, I could talk about the null set as being a subset of the power set or as an element of the power set. So note, when we're talking about as a subset, that's as the null set for the power set of X. As an element, we're talking about the null set for X itself. Now, one useful application of power sets, starting from the null set, we can build the natural numbers. So here we're able to get something from nothing. So let's see how we do that. Okay, and I'll just give a hint, we won't do a full proof. Now, if I take the power set of the null set, well, the only subset is the null set itself. And what I'll do is I'm going to assign a sequence. Okay, we'll just send the null set to 0. If we take the power set of the null set, okay, so what's happening here? So where are the subsets in here? Well, this is a 1-element set, so I can either have the set that has that 1 element, or I can have the empty set itself. Okay, note here, this empty set is not the same as the one on the inside. Now, assigning sequences of zeros or ones. Okay, so we're asking if this empty set's in the set or not. So for this one it is, so we'll assign a 1. For this one, it's not, so we get a 0. We take it one more level. So I'm going to take the power set of this set. So the power set of the null set. All right, what sets do we have here? I have the set with both elements. We have the subset with just the first element. We have the subset with just the last element. And we have the null set. So, assigning a sequence of zeros or ones to each of these as before. Okay, this one has in, so 1, 1. This one has just the first one in, so I'll have 1, 0. This one just has the second one in, so 0, 1. And then the null set itself gets a 0, 0. So we can continue playing this game by taking power sets. Okay, if we're careful with our bookkeeping, we can make it so that I generate every finite binary sequence of zeros or ones using this method. Now, every finite sequence of zeros and ones is going to correspond to a natural number if we convert from binary to base 10. So this is a way to construct the naturals from the empty set. Now, with power sets, we're considering sets that are elements of other sets. Okay, so here we're not talking about a set being a subset of another set. We're talking about it as being an actual element. We could run with this idea. So I could try to construct the set of all sets. So we would take any possible set that we can imagine, put them into one big superset. The question, does this set of all sets make sense? According to Russell's paradox, it doesn't. So what Russell's paradox says, we're going to consider the set S, okay? The elements of S are going to be all sets that are not elements of themselves. We then ask, is S an element of itself? So that is S a set that is not an element of itself? Now, I'll leave it to you to think about that, but you're not going to be able to reconcile that. We're going to have a paradox. So, one thing we're going to want in our set theory is this issue of regularity. So, we're talking about general sets. It's never going to be the case that a set is allowed to be an element of itself. Now, for us, it's not going to be a problem because usually we're going to be working with a concrete set, like the natural numbers, the integers, and so on. You'll note, in Russell's paradox, okay, part of the issue here is self-reference. We're defining S in terms of itself. We've seen self-reference cause problems before. For instance, with the statement, this statement is false. So again, here, we see that a paradox is going to result.